Okay, so in this last step, we are going to choose a kinematics equation and derive an equation that shows whether our relationship is proportional, squared function, or square root function. So we already know it's a square root function, but we're going to derive it from the kinematics equation. We're trying to link the relationship between delta xy and time. Okay, now there's a lot of different kinematics equations, right? I'm going to run out of space on this page, so let's go to a new page. So we have v equals v naught plus at. We have x equals x naught plus v naught t plus 1/2 at squared, right? And we have v squared equals v naught squared plus 2a delta x. Right, and don't forget, any of these equations could be vertical or horizontal. Because we're trying to establish the relationship between the launch height and time, right, we're going to make all our equations vertical. So for any of these variables, make sure that you are using the y value for all of them. The only one that doesn't have a y value is time. Time is not does not have direction. It's not a vector. So, which equation looks like it could link time and change in height? Well, definitely not this one, because there's no time, right? And definitely not this one, because there's no displacement. So we're going to use this equation right here. Now, our initial height was 0, right? And our initial vertical velocity was 0 because it was a horizontal launch. So that simplifies our equation. It boils down to final height is equal to 1/2 at squared. So, let's actually keep this part of the equation and do a little bit of math. So here we go. So we have I'm going to derive it. So x final equals x initial plus vi. I switched from not at squared, right? Instead of not, I'm using initial, is 0. I'm going to subtract xi from both sides of the equation. And now I just have delta x, right? That's our displacement. And then I'm going to end up with 1/2 at squared. Okay. Now, am I in the correct form? Y equals, well, delta x is the vertical height. That was our input. So that was actually our x value, and time was our y value. When we made our graph, we had time on the y-axis. So I need to rearrange this equation and solve for time to show that it's a square root function, right? We always want y equals, or f of x equals. So I'm going to rearrange this equation for t equals. So let's do that right now. So I'm going to multiply each side of the equation by 2a. No, sorry, I'm going to multiply each side by 2 and divide by a. All right, multiply by 2, divide by a. Why would I do that? Because 1/2 times 2 is 1. And then a divided by a is 1. So I'm left with t squared equals 2 over a times delta x. Don't forget that's delta x in the y direction. Okay, now I take the square root of each side of the equation, and on the left side I have the square root of 2 parts being multiplied together. I can separate that out as the square root of 2 over a times the square root of delta x in the y direction. On the right side, the square root of something squared is that thing, in this case t. So now I have my equation in the form of y equals mx, where I've graphed time on the y-axis, and on the x-axis I have the square root of x. Now you might say, wait a second, Mr. Hebert, we did not graph time versus the square root of x. So what am I trying to prove in this equation? In this equation, what we're trying to prove is that the nature of the relationship is a square root function.